Spring is upon us, and what better time of year than the spring to bring to life some new and exciting trig identities born from the old and worn rules that we're already familiar with. If we start with this rectangle that's been drawn with a couple of important triangles involved, there is a way to link together the two angles marked. We've got alpha, we've got beta, and then we've got the line AE with a length of 1. I'm not going to work through this in the video, I'm going to leave this as an exercise for you, but there is a sheet specifically for this, deriving the trigonometry addition formulae. If you work through each step and calculate the length of each line in terms of the angles, taking care with your right angle trigonometry, you should find you get a whole bunch of terms that involve sine alpha and cos alpha and sine beta and cos beta. And the trick with this is to compare the height of the rectangle on one side, BH, with the height on the other side, AG, and then also you compare the width on the bottom, AB, with the width on the top, GH, and you should find you end up with two completely different looking trig expressions in each case, but they're equal because they are opposite sides of a rectangle. It's a good way to work through and generate the two main addition formulae. So when you've had a go at that and you've worked through and you've found some results, come back to the video and see what comes next. So if you've found the addition formulae, a good starting point will be to say what can we do with them based on what we know. And this would be particularly useful back in the day before calculators could quickly and easily give you a whole bunch of different results to an arbitrary level of precision. If you've got certain angles that you know the trig results for and others that you don't, can you construct for yourself additional results? Sine of 165 degrees, for instance, if we have a formula that allows us to link the sine and the cosine of different angles together, we may be able to construct for ourselves a method for evaluating the exact result for sine of 165. Okay, so we have sine of a plus b. This is a standard addition formula. You do sine of one of the values, cos of the other one multiplied together, and then swap around, do cos of the first, sine of the second. Fortunately, you don't have to memorize this or the other addition formulae. What you need to be able to do is recognize them, use them fluently, confidently, and not get them the wrong way round. You also need to be able to derive additional results from them, make use of them occasionally in proofs, so they're worth being familiar with, but don't stress about memorizing every detail of it because it'll be in the formula book so you can double check it at the time. Now, the trick here is that we want sine of 165, but what we have is other angles. We've got 30, 60, 45. There's a few others that I've not included that are probably more obvious. Sine and cos of 0, sine and cos of 90 degrees, things like that. So if you find there are others that you can construct, then feel free to use those. I've gone with 120 and 45 because sine of 120 is an angle I can generate because I know sine of 60. 45 is an angle I already know from the half a square standard triangle. If we apply this, you can see we're just choosing a value for A and choosing a value for B and substituting them into the formula. If you do that, we get a bunch of surds and out pops a surd as our answer. You should find on your modern calculators you can put sine of 165 into the calculator, make sure you're in degrees mode, and it will give you this nice exact surd answer. Most older calculators won't do this, but even if you get an approximate decimal value, you can verify the validity of your result by checking to see what it will be as a decimal. I'd recommend you pause the video at this point, see if you can calculate the value of cos 165 using a similar method, or maybe see if you can find a different method, maybe using different angles to build it up. You might want to check to see how you can verify sine of 120. Perhaps you want to construct that from sine of 60 and sine of 60, or from sine of 90 and sine of 30. And then what about tan 165? If you've already got cos and sine, is there a way you can use just those sine and cos addition formulae to construct the tan of 165? And then I'd encourage you to have a think about what other angles could readily be derived by hand. If there's a certain few that you've got that you know, which ones could you construct if you had to by combining angles that you know? And which angles feel like you wouldn't be able to get them at all, no matter how much you manipulate and add your angles together? Now we're going to see what else we can derive from this identity. We've recognized, we've used a diagram to construct a proof for sine of a plus b. What I'd like to do now is try to figure out what we can do to get a similar result but a subtraction version of it. We're going to make use of the fact that sine is an odd function. That means it has rotational symmetry about the origin. In other words, if you reflect it in the y-axis, you get the same result as if you reflect it in the x-axis. And cos is an even function. It has reflection symmetry in the y-axis. So cos of minus 30 gives the same answer as cos of 30. Whereas for sine, if you try sine of minus 30, you'll get negative a half, which is the negative of sine of 30. We can use this fact because what I'd like to do is substitute negative b in place of b. And it ends up looking like this. Wherever we have b in the original formula, we put negative b, and that makes the left-hand side turn into sine of a minus b, which is what I want. On the right-hand side, I have various terms. It seems to work, it's given me a formula, but what I'd like to do is have a formula in terms of sine a, sine b, cos a, and cos b, just like the one above us. And to do that, I need to deal with the negative signs inside. Now, the sine function preserves the sign of whatever's inside. So sine of minus b will be minus sine of b, but the cos function absorbs the sign of whatever's inside effectively. So cos of x is the same as cos of minus x, it makes no difference. So we can just get rid of that first negative sign, but the second negative sign is preserved. And we end up with this, sine a cos b minus cos a sine b. And if you compare that formula to the original one, you'll see they're very, very similar. All the terms are the same. The only difference is that we have a minus in between the two terms instead of a plus. You can do a very similar thing with cos. I'd recommend you pause and have a quick go at deriving that. See if you get the same result that I do. Take care that you recognize which bit becomes positive and which bit becomes negative. And you should get this. Because the two terms at the beginning, the cos terms, are both cos A, cos B. When we change cos B into cos minus B, it doesn't affect things. But in the second term, where we have a sine B, it becomes minus sine B, because sine of minus B is minus sine B. It cancels out with the negative, and we get a positive. I want you to notice what's similar about these pair compared to the original pair. This pair have the same terms again, and the sign has changed again, but the difference is, with sine, the signs matched. So we had an A plus B, and that corresponds to a plus on the right hand side. Whereas as soon as it changed to a negative, we ended up with a negative on the right hand side. With cos, the signs don't match. The plus goes with a minus, the minus goes with a plus. So we get something which is similar and something which is different, worth bearing in mind. A nice simple way you can verify that these work is to try simple values. Just check for yourself. I've done sine of 90 minus 60, which should give me the same as sine of 30, and it comes out as a half, so I'm happy with that. You can try even simpler values, but just be a little bit careful. If you try values that evaluate to 0 too often, like cos of 90 is going to disappear, for instance, it does make the calculation a bit easier, but it may mean that you lose any useful information about whether it was a plus or a minus. So for instance, the example I've used, potentially, it's a bad example. If I'd accidentally put a plus on the right hand side, you can see it would still have given me a correct answer, but it wouldn't necessarily have alerted me to the fact that there was a plus in the middle. So be careful. If you're going to check with simple values, perhaps check with a few different ones or with not quite so simple values, so things don't all cancel out too trivially. So we've seen sine, we've seen cos, we've got pluses, we've got minuses, we haven't yet got a tan. That's the next thing to look for. But we know that tan theta is just defined as sine theta over cos theta. We can construct our formula by taking the sine A plus B formula and the cos A plus B formula and dividing the two. If you look closely, you'll see there's various things in here that look like they might cancel out. We've got a cos B on the top and bottom, sine B on the top and the bottom, so we can cancel those and we get sine A plus cos A over cos A minus sine A, right? Take a good look at that. If you're already shouting at the screen, then excellent. You've noticed what's wrong. If you haven't seen it yet, keep looking, because something is amiss. What I'd like you to notice here is that even if you've not recognized what I did wrong, hopefully you recognize that something has to be wrong because of the nature of this term. B has disappeared. Now, either the value of tan of A plus B is independent of B, or we've cocked up somewhere. Now, since we know that tan of 95 is different to tan of 100, and that tan of 32 is different to tan of 31, it can't be the case that B cancels out and disappears. In fact, you could construct from this all sorts of logical contradictions. So something has gone wrong. The question is, what went wrong? Why is that final line not valid? And a common mistake people make here is to notice there's a cos B top and bottom here and here, and to say to themselves, that cancels out. There's a big danger with using the phrase cancels out in this context. If you say cancels out, you don't explicitly alert your brain to the mathematical process that's going on. All you're allowed to do when it comes to simplifying fractions is multiply or divide by a common factor. If you don't have a common factor top and bottom, then no cancelling for you. We don't have a common factor here, but there is still something we can do to simplify. It feels like this is too messy. And it's all well and good having sines and coses of A's and B's. That's what we had before for the sine and the cos formulae. But it will be nice if we could write this in terms of tan. And it turns out we can. But if you look for a common factor, you won't find any. Sine of A, cos of B, cos of A, sine of B. Wherever cos A occurs, it only occurs in one of the terms on the top and the bottom. But cos A does appear on the top and the bottom exactly once in each, and cos B occurs on the top and the bottom exactly once. Same for sine A and sine B. So something's going on. There's a lot of symmetry in some sense in this expression. And if we're trying to get to something that only involves tan, that might give you a clue as to how we're going to proceed. If we have a term involving sine A, for instance, and we want it to involve tan, well, tan A will be a logical choice. But in order to get tan A, you'd have to have sine A over cos A. Okay? And that's not impossible. We've got a fraction. We could divide the top and bottom by the same thing. You could go through the entire thing and divide by cos A. In fact, if you did, that cos A term would cancel out. That'd be quite nice. This cos A term would cancel out. And then there's a sine A term here that would be dealt with quite nicely by dividing all terms, top and bottom, by cos A. So those two in the boxes would turn into tan A, and the two underlined would just disappear because you'd be dividing by cos A. And then look what you're left with. You have a cos B term and you have a sine B term. And you could do a similar thing with that. You could take each one of those and say, well, maybe if I divide every term by cos B, sine B will turn into tan B, sine B down here will turn into tan B, cos B here will cancel, and the cos B here will cancel. And that's exactly what happens. It looks horrible if you try writing it out like this, but you don't have to necessarily. You can write it a little more elegantly, or you can miss off certain bits. As long as you can see what's going on and you're careful with it, it's quite nice the way this works. We had exactly two terms in each case, and it's a whole bunch of different combinations of the sines and coses. I think of those four terms, you've got sine A appearing in two of them, you've got cos A appearing in two of them, sine B appearing in two of them, cos B appearing in two of them. And by dividing by cos A, cos B, everything cancels out on the bottom left term. So all of that disappears. On the top, cos B and cos B disappear. And over here, cos A and cos A disappear. And then in the bottom right term, nothing cancels out. So it's kind of all or nothing on the bottom, and it's half and half on the top. Sine A over cos A does exactly what we wanted it to do. Sine B over cos B does what we wanted it to do. And you end up with this elegant result. The sum of the two tans on the top, and then 1 minus the product of the two on the bottom. Here's a nice example of a question I just made up that I think works quite well to demonstrate why this might be useful. Because remember, tan of an angle is equivalent to, well, it's opposite over adjacent. That's the definition of gradient. If I tell you I've got a line with a gradient 0.5, what that means is the angle that corresponds to the slope can be found by doing inverse tan of 0.5. Now you can work that out if you like, and you get an awkward looking angle. It comes out as about 26.6 degrees. But that doesn't matter, because it turns out if all I care about is the gradient, I have the slope of two ramps, and I'm going to put them together so the overall ramp is going to be steeper than the original ramp. Well, I can get the steepness of the new ramp by combining the steepnesses of those. Tan of 0.5, sorry, tan of the angle of the first slope, tan of that angle will be 0.5. Tan of the angle of the second slope will be 0.75. And what I'm being asked for is tan of the angle of the overall slope. So if those angles are A and B, then the overall slope will have angle A plus B. But I don't need to calculate A or B to work this out. All I need to do is use the tan of each one. Tan of A plus tan of B over 1 minus tan of A times tan of B. And I get a really elegant answer. Instead of all that faffing around with tan and inverse tan, we can get those numbers directly. It's quite nice. I like it. Now, I just want to conclude this bit by looking at the tan A minus B formula. You'll notice something funny has gone on the top. I've got this plus minus term in there. That's an elegant way to incorporate the fact that the sine A plus B and sine A minus B formulae are very similar. The only difference is the sign in between the two terms. So when it's A plus B, we have sine cos plus cos sine. When it's sine minus B, we have sine cos minus cos sine. Similar thing happens with cos, but the other way round. That's why this one says minus plus instead of plus minus. That's telling you that the plus on the left corresponds to having a minus on the right. And similarly, with a minus on the left, a plus on the right. We can incorporate that when we figure out what's going to happen with the tan formula. It's not necessary to do it like this. Another way is to work out whether tan is an odd or an even function. Some functions are neither, but tan happens to be one of those. So, and you can derive that directly from the fact that sine is odd and cos is even. But whether or not you know what tan of minus theta would be, whether it's tan of theta or minus tan of theta, we can derive directly from these things because the top of our fraction came from the sine and the bottom came from cos. That means the sine is preserved on the top, which is what we can see here. When it's tan A plus B, we get a plus on the top, and the sine is reversed on the bottom. When it was a plus on the left, it was a minus on the bottom. When we put that through, we get tan of A minus B, we get a minus on the top, we get a plus on the bottom. So the sine is preserved on the top and reversed on the bottom. This is what you'll have in the formula book. This is essentially all 6 trig identities. We've got every single thing in here, but it's summarized using the plus minus and minus plus notation, just as you've seen before. The plus minus on the top and the minus plus on the bottom of the tan one will act as a reminder if you're asked to prove the tan addition formula. You can do it using the sine and cos and the method we've used, and it will remind you need to be dividing one by the other. And if you remember that trick with dividing by cos A and by cos B, all terms top and bottom, you'll be able to derive that without any trouble. The final caveat that they've got going here is a complicated way of saying avoid asymptotes. In other words, it's not going to work if the denominator of your fraction is 0. This is going to give invalid results if you try it for angles that have a sum of 90, or if you're doing the subtraction one, angles that have a difference of 90. Going to do another quick example with tan because it's so nice. If you have a wooden wedge with a slope of 0.6, so the opposite side is 0.6 times the adjacent side, we want to bisect the angle, so we have 2 wedges with identical angles, and we want to know the slope of each wedge. It's tempting to think it's going to be 0.3, but that's not how these things work. If we use our tan A plus B formula, this time you'll notice I've got something slightly different. This is a precursor to what we're going to come on to shortly, which is double angle formula. Here we want the angle to be the same for each of the 2 new wedges, which means that A and B are basically the same. I've called B A, and A is still A, so we have tan of A plus tan of A, and 1 minus tan of A times tan of A. The result will be tan of A plus A. Well, that's the slope that corresponds to both angles together. That's the original slope. So whatever that is, we know it's going to be 0.6. I'm also making life a little bit easier by referring to the slope of each new wedge as x. The slope of each new wedge is tan of the angle of each new wedge. So that gets a value x. I'm going to call that x. That means I've got 2x on the top and 1 minus x squared on the bottom. And that starts to look a lot like a quadratic equation. Do a bit of rearranging, you can solve, you'll find that one answer makes sense and the other one doesn't. We know that the slope of each wedge will be positive because it's a physical wedge of wood, it's going to have a positive angle, and we come out with a positive gradient for it. Remember, this 0.277 is not the angle, it's the slope. I never needed to work out the angle. I never worked out what the original angle was by doing inverse tan of 0.6, and I never worked out what the new angle was by doing inverse tan of 0.277. But if I had, I should find that the angle I generate from inverse tan of 0.277 is exactly half the size of the angle I get from inverse tan of 0.6. So you can verify it with the calculator, but it's nice to be able to calculate these things directly without having to go back and forth between the angle and the trig ratio of the angle. Okay, there are questions that you can work on the sheet that you hopefully already have in front of you from deriving trig identities. These should look familiar. You can work through some of these for yourself. In particular, questions 3 and 4 and 5, I'm going to talk through a little bit more on here. So I recommend you have a go at these questions, at least give them a stab before you watch the rest of the video. There are also a number of questions you'll find helpful to try in the textbook that you can do either now or after you've watched the rest of the video. Right, so the double angle formulae. Hopefully you've had a chance to derive some of these if you've tried the later questions on the sheet. But we're going to go through them together now so you can see exactly how it works. It's worth bearing in mind you will be provided with the trig identities as shown in this corner, but you will not be given the double angle identities. What you get are the addition formulae, and the double angle formulae are derived from those. The addition formulae are very powerful. They can be used in lots of different places. We'll see some examples of how they can be used to solve equations that are otherwise unsolvable. And one of the useful things we do with them is this sort of subset of the addition formulae. Instead of just saying what happens when we have two different angles added together, we say, well, what if those two angles are not necessarily, well, not different, but perhaps they're identical? Then we get the double angle formulae. Instead of sine of A plus B, we're saying now it's sine of A plus A, essentially. Similar to what we did when we were breaking the wedge in half. We can start with the sine A plus B formula, and then we set A and B both equal to the same value. This is a process you'll need to be able to follow for yourselves. You need to be able to derive these directly from what's provided for you in the formula book. Sine of theta plus theta is sine 2 theta, and on the right hand side, because A and B are now the same, sine of A and sine of B are the same term. They're both sine of theta. So we can combine those and get a slightly more elegant looking formula. Sine 2 theta equals 2 sine theta cos theta. If you haven't yet, check that you can derive the formulae for cos and tan doing a similar process. And when you've got a formula, see if you can rewrite it in any different ways. Because although sine 2 theta has an obvious simplification, and it doesn't get much simpler than 2 sine theta cos theta, for cos and for tan, there are a couple of different ways you might be able to write your formula, and some of them are more useful than others depending on the situation. When you're done, unpause and we'll look at what they look like. Okay, here's our double angle identities. We've got sine 2 theta already. Cos 2 theta has two variants which will come in very handy. It turns out, because the cos formula involves a cos and a cos, that turns into cos squared. The sine term turns into sine squared, and because we already know that sine squared is 1 minus cos squared, and equivalently the cos squared is 1 minus sine squared, there are two alternatives that we can create, both of which are really useful, particularly when we get later onto calculus, in particular when we're integrating trig functions. These two identities come in really handy. Turns out it's pretty straightforward to integrate cos 2 theta. It's not straightforward to integrate cos squared theta or sine squared theta. So rearranging these identities so that we can integrate sine squared or cos squared theta comes in really handy. You could rewrite the tan 2 theta formula. You could have a 1 plus tan theta times 1 minus tan theta on the bottom if you like. It's not usually done. Generally speaking, this format is sufficient, and if you want to do more things with it, then you could. But it's quite helpful for it to be written in a form that only involves tan theta rather than sine thetas and cos thetas, of course. The tan 2 theta formula you will see more of when you do further maths. There's an entire section called the half angle formulae, where they make a very slight change. They replace 2 theta here with theta, and therefore they have to replace theta here and here with half theta. And that means that you can then write tan theta in terms of tan half theta. Seems like it will be a fairly pointless exercise, but it turns out to be incredibly helpful for proving all sorts of trig identities, and most usefully for dealing with integration problems or differential equations problems that involve trig and are too hard for us to make sense of how to interpret or extract. There's a few identities you can derive from the half angle formula for tan, which then allow you to deal with sine and cos and tan and so forth. So that's a useful one to be aware of. We'll be coming back to tan 2 theta in due course. The final thing I want to look at is the COSSquared graph. It's an interesting one. If you try sketching y equals cos squared, there's a few things you should notice initially. If you haven't tried it yet, pause, give it a go, do a sketch by hand, think carefully about the shape of the curve as well as where it might go and how often it wobbles, and then try it on GeoGebra and see what you notice. If you're curious, you can try cos cubed and cos to the 4, and you'll see they come out looking rather weird and different, but there's something particularly special about cos squared. Not only is it always non-negative, because if cos is negative, cos squared will still be positive, but because of the way squaring works, when you're squaring a number less than 1, it has the effect of stretching in the downwards direction. So if you square a half, you get a quarter, and if you square 0.9, you get 0.81. So it's dragging the numbers down, but it drags them down more when they're close to 0. If you square 0.1, you get 0.01, so a tenth becomes a hundredth. That ends up giving you a weird sort of graph. This isn't it. We're going to get to it. This one's cos x. But hopefully you can see that there's something about cos squared that makes it look a lot like a cos x graph, but with a few changes. So we're going to see what kind of changes you'd need to make and see if we can figure out why. First of all, when you do cos squared, you notice that it wobbles a lot more than cos x. In other words, it has a greater frequency. It goes up and down quite a lot more. So the first thing I'm going to do is a stretch of scale factor a half in the x direction. This gives me cos of 2x, and that gives me an increased frequency. Now it does a complete cycle in a 0 to pi rather than 0 to 2 pi interval. The next thing I want to do is recognize that my cos squared graph, if you're looking at it, is smaller. It's got a lower amplitude. It goes between 0 and 1, because obviously if you square a number between -1 and 1, you're only ever going to get values between 0 and 1. So I'm going to emulate that by performing a stretch of scale factor a half in the y direction. Now my graph starts to look a lot like the y equals cos squared graph. The final step I need to follow is to move it up, because right now it goes between a half and minus a half. And if I do one final step, translate vertically by 0 a half, so it moves up a half, I get cos squared. You can look at the shape and see how it matches with cos. It's more gradual. At the point where it's 0, it's distorted downwards because it's been squared, but it absolutely is just a series of linear transformations from a cos x graph. I find this quite delightful. What I want to notice at this point is why that identity should be true. Hopefully you've recognized there's a connection going on there. But if we look at a half cos 2x plus a half, and then we look at the cos 2x written in terms of y, rearranging that final line gives me cos 2x as 2y minus 1. But y itself, well, hopefully by comparing the two lines we've got here, you'll see what y has to be, because all I've written down here is the identity for cos 2x. Cos 2x is always the same as 2 cos squared x. So technically this should be an identical to symbol. If those two are always the same, then it stands to reason it must be the case that y and cos squared x are the same. What I've done by distorting the cos graph into this half cos 2x plus a half graph is I've turned it into the cos squared graph. They are exactly the same function. You could, of course, do a similar thing by starting with a sine graph, and you would end up with 1 minus 2 sine squared x. I'd encourage you to give that a go, play around with GeoGebra, see if you can make your graphs do interesting things. And if you're curious, you can try playing with a cos to the 4 graph and see if you can construct some more elaborate things. The world's your oyster now. You've got addition formulae and double angle formulae. Some suggestions for what you might do to extend. See if you can create for yourself a triple angle formula, cos 3 theta or sine 3 theta, and see if there's anything elegant you can find out about the quadruple angle formulae, cos 4 theta. Turn that into something involving only sine and cos of theta. Once you've got those, maybe you can find a way to construct more and more angles directly by hand. If you notice, for instance, this particular formula, cos 2x in terms of cos squared x, that should allow you to construct the size of, let's say, cos 15 just by knowing cos 30. Cos 30 is cos of 2 15s, so cos 30 must be 2 lots of cos 15 squared minus 1. By doing a little bit of rearranging, we can find the value of cos 15 directly from that insert form. There'll be a bit of square rooting involved. You might get the square root of a square root in some cases, depending on what angle you're starting with. But there's a lot you can do with that sort of thing. Have fun.